First was electrostatics. After electrostatics, we did capacitance. And it's actually called capacitance and dielectrics. Then current and resistance. Then magnetic fields. And finally, induction. Those are the 5 units. Your problems have slowly built off of those 5 units. But in each case, there is a collection of kind of banner things that you had for each. Unlike mechanics, where although there are 7 units in mechanics, there's really only 3 major units in mechanics. Dynamics, which is Newton's laws, work and energy, and impulse and momentum. And everything can kind of boil down to those 3 things with some ancillary things on the side. Rotation being a rehash of all of it. Kinematics being the result of dynamics. I mean, those things are ancillary to the subject. There's really only those 3 units. Here, it's harder to see when you look at a problem, some of the delineation. These are more rigid, and you know that. For example, electrostatics is Coulomb's law. Right, that's where we started. We'll bring back our friend K, remember? Long before we had Gauss's law. It also developed the concept of the permittivity constant. That comes from Gauss's law. And that there's something about electric fields in free space that's necessary to understand the way electric fields are established. Also the definition of charge. Something that was elusive. And even today, I'm not sure we can define it. We just know kind of how it behaves. We had Gauss's law. And the first introduction to the term flux. Unit 2 really was about developing the concept of energy and how energy plays a role in electrostatics. Before we could get there, we had to kind of take a moment and understand that energy might be something within the electric field. And we talked about doing work. Again, introducing a topic from mechanics. So we had to remember things like, and I want to do it the same way over here, but there's really only 3 for mechanics. Because we defined the electric potential as work over charge, we had to bring back the concept of work. When we discussed how to find the electric potential, can't believe I'm having to scroll up, we did so relative to the field. You could do work by moving a particle through an electric field. Now that ended the conversation of electrostatics. That was the end. And it pains me that not all those fit on here, so I want to get them all on there. There we go. So the whole page is kind of used. Mr. Sheldon, be better. Yeah, just going to be weak. I'll be weak. There. The next topic was capacitance, and we wanted to learn how to store energy, and we wanted to do it in an organized way. We defined capacitance based on the manner in which charges could be moved from one conductor to another. Remember, in all of this isn't just the equations. In the middle of all of this is the idea of how charges are distributed and how some materials deal with charges versus others. So what's left out of this list, because it's not an equation, is a difference between an insulator and a conductor. Something that probably should be in your notes, but doesn't really fit conveniently into these categories when it comes to what are the topics being taught. So capacitance we defined as how much charge you could store per potential difference. So if I have, yes?
Can you do anything about the potential inside of the conductor?
Yes. You should be able to calculate it, but the thing to understand about, now this led us to requiring you to have a procedure to calculate the capacitance of a some kind of symmetrical system. Do you guys remember doing that? There are 3 symmetrical systems to which you are supposed to be able to calculate: the parallel plate capacitor, the cylindrical capacitor, and the spherical capacitor. The most important one, of course, is the parallel plate capacitor, because it represents the one that makes the most number of appearances in our day-to-day activities. But I want to remind you that it was a 3-step process to calculate the capacitance of some kind of charge distribution on 2 conductors. The first thing we did was set the charge to Q, meaning we just said there is a charge of positive Q on one conductor and negative Q on the other. So we established an initial amount of charge. To give myself much room to write. The second thing was we derived an expression for the electric field due to the charge. Then using that electric field, we calculated the change in potential going from one of the metals to the others. The whole idea was to utilize C equals Q over V. We set this one, calculated that one, and when we produced the quotient, we got an expression for C. The Q always canceled out. What we were left with was something that was geometric in nature, meaning it talked about the geometry of the object and how it was related to storing charge. Now, ultimately, your ability to calculate capacitance based on the shape there are only going to be 3 different shapes, right? And you should already internally have an idea that you should know, maybe in your head, what is the capacitance of a parallel plate capacitor, what is the capacitance of a cylindrical capacitor, and what is the capacitance of a spherical capacitor. And if you remember when we did these all, find them in your notes. Take a quick review. What's the most likely one to show up on the exam? Probably parallel plate, followed very closely by cylindrical. Cylindrical was on it just 2 years ago. And it makes an appearance every 3rd year or so. Now, I do want to remind you that we did also do simple capacitor circuits without resistance. And we talked about capacitance in parallel and capacitance in series. We talked about systems of capacitors. And finally, we talked about dielectrics between the plates of the capacitors. In fact, I think if you'll remember, one of your least favorite things at the time was dealing with, say, a system where we had a simple parallel plate system, and maybe there was a dielectric of one type filling this portion, and of a different type filling this portion, and of a different type filling this portion. You guys remember those? And that's kind of what we culminated with. Always, always, with any of our devices, we talk about energy. If not energy, the use of energy. After that, we took a reprieve, talked about current as the flow of charged particles. We talked about resistance and Ohm's law. Made it very clear that resistors use materials that have resistivities, and that the size of a resistor is also based on a physical set of properties. That a resistor is made of some material that has a resistivity, and the size of the resistance is based on properties of the physical size of the material. So how long it is versus its cross-sectional area. With cross-sectional area making the resistance smaller and length making the resistance longer. We use the analogy that resistors in series would have more resistance, and that's why resistors increase their resistance with their length. And having more resistors in parallel decreased resistance, which is why having a larger cross-section allowed the flow of more charges decrease the total resistance. But that also gave us the capacity to deal with our first actual circuits that dealt with the flow of charged particles, parallel and series circuits. And we talked about stepwise reduction, and we talked about Kirchhoff's laws. So, aside from the obvious, we said that Kirchhoff's laws said that the sum of the voltage drops equals 0, and current in equals current out in any junction. The first one is a statement of conservation of energy. The second one is a statement of conservation of charge. And that those two laws could be used to solve any circuit, but they get complicated, so we tended to find shortcuts. Stepwise reduction was a shortcut. So for circuits that we could do stepwise reduction, meaning reduce it to a more and more simple circuit using equivalent circuits or equivalent resistances, that's what we did. But then we ended this unit with the RC circuit. And then we had a break, which we all enjoyed, and then came back to magnetic fields. Magnetic fields represents dynamics, right? Everything about magnetic fields was about movement. So either in order to experience the force from a magnetic field, you had to be moving, and in order to generate a magnetic field, the charge had to be moving. But everything about magnetic fields was about movement. The simplest was to remember that F equals QV cross B, or F equals IL cross B. The force on moving charges, either free moving charges with QVB, or charges that were trapped in a wire, ILB. This is also where we get Biot-Savart, where the creation of a magnetic field comes from the production, comes from the motion or the movement of charged particles. If you remember, it's something like DL cross R hat, can't really fit it in there, divided by R squared. The Biot-Savart law. Am I saying it wrong again? I hope so. There's no E at the end, right? It's S-A-V-A-R-T, not S-A-V-A-R-T-E. Just making sure, because I'm going to spell it wrong next year, and I'll make them correct me, because I'll forget. I don't remember things. Truthfully, we also talked about that a single charged particle moving through space would also produce a magnetic field, but it's relatively transient, because that magnetic field builds up around that particle, but then goes away when the particle goes away. We made lots of references to this net force being equal to MAC on a free particle. Do you remember that too? That free particles moving through a magnetic field move in circular paths because that force is perpendicular to the direction of motion. This is where we also developed the idea of the right-hand rule, a method for determining the direction of that force due to the motion of the particle and the direction of the magnetic field. And although it felt relatively light on content, we also had things like parallel currents attract and anti-parallel currents repel, stuff like that. Remember all those fun times? I do. Not really, but I do. The thing about magnetic fields that I found interesting was that at the end of it, when we were talking about the stuff about magnetic fields before we got to induction, was if you're moving along with the particle, are you experiencing a magnetic field or a force from a magnetic field, or are you experiencing a force from an electric field? That frame of reference is pivotal in understanding whether you're experiencing magnetic forces or electric forces. In fact, we didn't fully develop that idea. I'm waiting for a day when we can. But they're the same force, or maybe the same field. It's just about your point of reference. In fact, relativity is a part of a discussion about magnetic fields versus electric fields and the way in which they apply forces. The only thing that is truly real, and I mean this in a metaphysical sense, the only thing that is truly real is the effect on an object. A force causes a change. Is it coming from a field? Well, perhaps. That's our theory. We believe fields exist. But the only thing that we can physically measure for real is a force. We can see the effect of that field that causes a force on a particle. We say a field is what's causing it. This is also where we get Ampere's law, that I enclosed is equal to, mu naught times I enclosed is equal to some kind of Gaussian loop. And we say it's the magnetic field dot ds through a closed loop around a current. It was an easier way for us to calculate the magnetic field. If the magnetic field from Biot-Savart is Coulomb's law, then using Ampere's law is Gauss's law. Induction was an extension from our conversation about the force on charged particles. We called it motional EMF. And we started the conversation by just having a bar pass through a region of space with a magnetic field. We said that bar would move charges, the magnetic field would move charges within the bar, creating a potential difference inside the bar. And we said that we call that a motional EMF. Faraday took that idea and extrapolated it to a more, a more elegant approach, saying that an EMF is equal to minus N times the magnetic flux. I didn't write that right. Minus N times the rate of change of the magnetic flux. And that magnetic flux, like electric flux, was how much magnetic field passed through an area. It's not a closed loop because we don't talk about a bounded area. We talk about a loop of current or a loop of wire being impinged on a magnetic field. And any change to the flux caused an EMF. Every part of this had value, with N being the least important. N represented the number of loops. The negative sign, though, represented Lenz's law, giving us the direction of the induced current. I know it's an EMF, and that was often troubling for us because we know a current would be produced because of that EMF. And currents were traveling through the wire, and we used the current as our guide for what the direction of the EMF was. But ultimately, Faraday's law is about EMF. Using EMF, using things like solenoids and other devices, we talked about inductors. And an inductor is a device that is used to store energy in a magnetic field. We didn't always write inductance the same way. We talked about the voltage drop across an inductor is equal to L di dt. But inductance was defined as the potential difference divided by di dt. And that is measured in henries. I didn't say farads earlier when I talked about capacitance. From here, we talked about RL circuits. And lastly, LC circuits. And although I don't expect you guys to be particularly proficient in coming up with the second order differential equation for LC circuits, you should realize that the mechanics kids all are proficient at dealing with simple harmonic motion. So your capacity to recognize that in a circuit is probably going to be tested, even if it's just a single FRQ. It's worth remembering that it's not particularly hard to calculate that the angular frequency is equal to 1 over the root of LC. That's in radians per second. Now, there's more. I mean, obviously, none of the intricacies is in here. And none of the subtlety is in here. But this is an overview of the year. And why I'm putting it up there is I want you to have something. I'm building this same kind of thing in mechanics, but I want you to have something when you're faced with a test, which is going to cover the entire range of these problems. Generally, unlike mechanics, which it's easier for them to join some of the things together, your test will probably be broken up into 3 very specific categories. There's going to be a circuit on your exam. There's going to be a circuit. That circuit could be any one of the 3 that are mentioned here. It can be a pure resistor circuit, an LC circuit, an RL circuit, or an RC circuit, but there's going to be a circuit problem on the test. There is very likely going to be an electrostatics problem on the test. And electrostatics really covers these 2 things, not just one. So if they're going to have a pure capacitance problem and not an RC circuit, it'll probably be lumped in with the inductor circuit. There is likely to be an induction or a magnetic field question on the test. That's how they tend to break the test up. 3 FRQs, 3 basic problems. Sergio? This would be stuff like a linear charge distribution, a long line of charge, or a surface charge distribution, a sheet of charge, or some kind of volume. Oops, different characters here. There. Oh, what am I doing? There. So I'm seeing that there's probably those 3 things. The line of charge we know to integrate's pretty tough, and a sheet of charge and a volume of charge even tougher if we don't use Gauss's law. But I still think we need to set those problems up. And also, remember this lovely thing that we had a couple times. Let's see if I can draw it. How about a ring of charge with a point located off-center on it? You guys remember problems like that? Can't use Gauss's law because they don't have the kind of symmetry that we would need. You would still have to be able to integrate that, which means remembering that we can write both the force and the electric field from Coulomb's law as a differential. And that to find the electric field required us to integrate. What we never dove into, and this was on purpose because I save it for second semester almost every year, is non-uniform charge distributions. So we did a uniform charge distribution just the other day. That was the insulator that was charged with the insulating shell around the outside of it. It had a uniform charge distribution, meaning the charge was the same everywhere within the insulator. I never presented non-uniform ones. I thought the uniform ones were tough enough at the time. My expectation is that you have now made it through another course of mathematics and you have a skill set that should allow us to dive into those. Now, I know when we talk about insulators versus inductors, what's the biggest, not inductors, conductors. What's the biggest difference between them? What's that? Partially where the charge is stored. In an inductor, charges stay where placed. If you have a distribution of charges in an insulator, that charge distribution stays there. The charges don't move around. That's not true for a conductor. The big takeaway for a conductor, and this is true for all conductors, is that inside the conductor, the electric field is 0. The charges will constantly reconfigure their location in the conductor to maintain an electric field of 0 and an electric potential that's a constant. And lastly, all charges move to the outside. right? Always move to the outside of the conductor. They rearrange themselves so that the inside of the conductor has an electric field of 0. It doesn't matter how much the conductor is charged, even if it's neutral or if it's fully charged, the inside of the conductor will have an electric field of 0. And that doesn't mean that there aren't competing electric fields in there. We talked about that too. That if you have an electric field moving in space and you have a conductor, what's going to happen is the conductor's charges are going to reconfigure to create an electric field that completely counters the external electric field, which gives you a net electric field of 0 inside the conductor. These are definitions, but we know how important knowing this is to the application of the rules. That question is, if I have a conductor that of any shape, so it doesn't matter what the shape of the conductor is. Now, we haven't talked much about this because it's a relatively obscure topic, but we did discuss it, and we took one day, so it was a long time ago. Inside the conductor, the electric field is 0, and the potential is a constant. That's a consequence of the definition of electric potential. That it takes no work to move inside a conductor to another point inside the conductor. Thus, the electric potential is 0 inside the conductor. The electric potential outside the conductor isn't necessarily 0. The electric potential on the surface of the conductor has to be the electric potential that's inside the conductor. But the electric potential just off the surface doesn't have to be the same as the surface. A complicated shaped conductor like this may have areas where the electric potential spikes just outside of the surface of the conductor because the charges are not uniformly distributed on a non-uniform conductor. That's a complicated sentence, but basically what I'm saying is because this conductor is weird shaped, in order for the charges to configure themselves in such a way that they make the electric field 0, there might be higher places where there are concentrations of charges and places where there are lower concentrations of charges. And because of that, the charge distribution is odd around a weird shaped conductor. Is that okay to answer your question?